opposite to matter, literally. For every subatomic particle, such as an electron, a proton, a neutron, etc., there exists an antiparticle such as an anti-electron, antiproton, and antineutron. The antiparticle will have the same mass as the particle, but it will differ in the sign of its charge and other quantum numbers. Some of these quantum numbers are the lepton number, 1 for the electron and each of the other 5 members of lepton family, and the baryon number, 1/3 for each of the 6 quarks that make up the baryon family. Antiparticles are expected to interact with other antiparticles in exactly the same way ordinary particles interact with each other. The laws of physics are almost symmetric when it comes to matter and antimatter. In fact, a universe made up of antimatter would be indistinguishable from ours. Going into a little bit more detail, the anti-electron is called a positron for positive electron, and it is positively charged with a lepton number of -1. The positron has exactly the same mass as the proton. The proton is a positively charged subatomic particle made up of 3 quarks, giving it a baryon number of 1. Its antiparticle, the antiproton, has the same mass as the proton, but it is negatively charged with a baryon number of -1, -1/3 contributed from each of the 3 antiquarks that make up the antiproton. Neutral subatomic particles, such as neutrons, are interesting. The antineutron has the same mass and 0 charge as the neutron, but it will have a baryon number of -1. Again, -1/3 coming from each of the 3 antiquarks that make up the antineutron. So what happens when matter and antimatter interact? The answer is fireworks. When a positron interacts with an electron, they both annihilate to produce 2 X-ray energy photons. So we are in luck that antimatter is so scarce in the universe nowadays. Otherwise, we would have been burned by X-rays and gamma rays every time matter and antimatter interacted. As a matter of fact, if you were to meet your anti-self, then both of you would annihilate and release the equivalent energy of roughly 2,500 megatons, almost 1/3 the total energy of the world's arsenal of nuclear weapons. Antimatter could sure make a mighty powerful spaceship engine, if you can find a way to produce macroscopic amounts of antimatter and a way to store it in isolation. Some modern particle accelerators regularly produce antiprotons for use in high-energy physics experiments. Now that we know what antimatter is, let us see how physicists discovered it. Back in the year 1928, Paul Dirac, one of the founding fathers of the new science of quantum mechanics, was trying to solve an equation that included the effects of the theory of special relativity to describe the behavior of electrons in the microscopic world. To his surprise, the equation admitted solutions that corresponded to electrons with negative energy going back in time. Any insecure student of physics would have blushed with embarrassment and redid the math. However, Dirac was sure of his math. Instead, he reinterpreted his problematic solution to denote an anti-electron with positive energy going forward in time. 4 years later, an experimental physicist by the name of Carl Anderson proved Dirac right by actually observing the anti-electron, the positron. The discovery of the positron earned Anderson the Nobel Prize in 1936. Dirac had already won the Nobel in 1933 for his contributions to atomic physics. Are you wondering where Anderson's positrons came from? The positrons that Anderson discovered originated in atmospheric showers of subatomic particles that result when very high-energy cosmic rays, mostly protons, interact with atoms in Earth's atmosphere. The story of the prediction and subsequent discovery of the positron is instructive and shows how big discoveries in physics are often made. The device used by Anderson is called a cloud chamber and was a standard instrument used in nuclear physics labs at the time. A particle going through a cloud chamber would leave sort of a trail of bubbles in its wake. Applying a known magnetic field would curve the particle according to its charge. The positron in Anderson's cloud chambers curved in exactly the same way as electrons, but in the opposite direction. As a matter of fact, these oppositely curving tracks were observed several years before Anderson at around the time of Dirac's prediction. but none of the physicists who observed them pushed the issue further. It was Anderson who persisted and tested and retested his results, and thus confirmed the reality of positron. This is in a way similar to Dirac when he came across his negative energy electrons. He did not simply brush the solutions aside as a mathematical curiosity, but instead reinterpreted them in a way that made us discover a completely new side to the universe. You can discover other sides of our universe. Right now you're probably wondering if antimatter has any useful purpose at all, apart from allowing physicists to learn more about the universe. The answer is yes. Every time a patient undergoes a so-called PET scan to detect tumors in the body, antimatter is involved. PET is an acronym for positron emission tomography. The patient is injected with radioactive sugars that accumulate at tumor sites. These radioactive sugars then gradually decay, emitting positrons in the process. A specialized and highly sophisticated instrument then maps out the locations from which the positrons are emanating, thereby giving a highly detailed view inside the human body. Patients who have had PET scans remain radioactive for a few days and are usually advised to stay away from children and pregnant women, given the risks posed by radiation to children and fetuses. Okay, so we now know what antimatter is. We know how it interacts with matter. We know how to produce it here on Earth and how it is produced in nature, basically under very special conditions and in very small amounts, and that it exists for a very short period of time because it interacts quickly with ordinary matter. But what we still don't know yet is why all stuff in the universe, planets, stars, galaxies, are predominantly not antimatter. This issue is so important in physics that it even has its own name, the matter-antimatter asymmetry problem. Addressing this issue requires that we delve into cosmology and high-energy physics known as particle physics. Full disclosure, the solution to the above problem is still being worked out by physicists as we speak. Nevertheless, we will try to get a very simplified version of the known parts of the answer. The theoretical framework within which to understand the matter-antimatter asymmetry is three-pronged and was formulated over 50 years ago by physicist Andrei Sakharov. Our quest begins right at the beginning, the Big Bang. The Big Bang is the instant when our universe was born. The Big Bang created equal amounts of matter and antimatter. For every electron there was a positron. For every quark there was an antiquark. Mind you, protons and neutrons formed much later. They formed a few minutes after the Big Bang, at which time almost all antimatter had disappeared. But we are getting ahead of ourselves here. Let's go back to the Big Bang. During the first fraction of a second after the Big Bang, the universe was an extremely hot soup of particles and antiparticles and intense radiation.